charge on this one? Does it become net positive or net negative? I took one electron from here, and that electron is now here. Negative. Electrons are negative. So this becomes minus. And how about this one? Yeah, it becomes net positive. Let's remove one. Repeat the process. Do it for the second electron, and the third one, and the fourth, and the fifth, sixth. Okay? So repeat the process. So till this one becomes net positive some number, and this one becomes net negative some number. How many times do we want to repeat it? Yeah. Huh? Yes, it's exactly that, but I'm just drawing the side. Yeah. So, so let's say somebody does this process, removes 10 to the 11 electrons. I'm using that number because my example has that number. So 10 to the 11 electrons, we place 10 to the 11 electrons here. 10 to the 11 electrons. Okay. And the question is, this one is going to be positive Q, and this one is going to be minus Q. What's the total charge if we remove that many electrons? What can I say about Q? It's going to be positive, right? Or negative? Yeah. So how much?
10 to 11 times mass.
Okay, it's going to be the number of electrons I removed times the charge of each electron, right? Which is E. Right? Plus or minus, right? Could be plus or minus. If you're adding the place that's receiving those electrons, it's going to have a minus sign in front. The place that lost the electrons is going to be plus. So capital N is going to be the number I removed, and then E is what's the charge of one electron or a proton? What's the magnitude?
1.661.
Oh, I think it's 1.661. Thank you.
Oh, yeah.
This one is the charge.
1.602.
That's the minus 19 coulombs. C for coulombs. So when you multiply, you get 1.6 times 10 to the minus what, 7? Or 8? Or 8. 8. Minus 8 coulombs. That's how many coulombs we have. So the plus one has 1.6 times 10 to the minus 8 coulombs. And the minus one will have minus 1.6 times 10 to the minus 8 coulombs. Okay. Next question is, what is sigma in this case? What's the charge density? Assuming the plates are, those are they're half a millimeter away, and then 10 by 10 centimeters.
It's PQ.
Huh? Okay, it's going to be what? The total charge, which is Q over what? Over area. Yeah, over area. Okay, so Q is 1.6 times 10 to the minus 8 coulombs. What's the area? It's 10 centimeters by 10 centimeters, right? So it's, yeah, we need to convert it to meters, right? 10 centimeters is a tenth of a 0.1 meters. So it's 0.1 by 0.1 meters, right? The area is going to be 0.1 by 0.1. So 0.1 meters by 0.1 meters. I usually don't write the units, but that's right. Oh, yes. So do that, you get what now? 1.6 times 10 to the minus what? Oh yeah, okay. I was ahead of myself, I guess. Coulombs per square meter, right? It's charge over area, coulombs per square meter. Before I go on, in what direction is the electric field outside of the two plates? 0, but they're not infinite. It's large enough that we can use the approximation. Same thing here. How about here? In what direction?
To the right.
Right. Yes. The electric field is going to be this way, right? Everywhere to the right. So that's the electric field. Now the question is, how much is it? That's right. It's going to be
sigma over epsilon.
Yes. Good. Each of them produces sigma over 2 epsilon naught. Combined, you get this. So 1.6 times 10 to the minus 6 over epsilon naught, which is 8.85 times 10 to the minus 12, right? So the electric field is going to be something times 10 to the fifth. Yeah. I think I can keep up with this. Or do I have to? Okay. No, I don't have the numbers. I need help.
One point.
That's the
1 point what?
1.8. 1.816.
1.8 times 10 to the. Shift it to the fifth because
Yeah.
this one is less than this. Is it 1.8? That's
1.82.
1.82. All right. Okay. The next thing I want to ask is, what are the units?
Oh.
What are the units?
Newtons per coulomb.
Newtons over C.
Yeah, newtons per coulomb. Remember, QE is the force. The charge times the electric field is newtons. So coulombs times the units of electric field needs to give you newtons. So newtons per coulomb. In a couple of chapters, we will have the unit called volt. It's going to be also volt per meter. Volt per meter is the same as newton per coulomb. You'll see that. So that's that. So yeah.
So if we expand the gap between the sheets,
Yeah.
so it's no longer infinite, right?
Yeah, if you make the gap so big that the area of the plates is much smaller than the gap. Then,
So we are no longer using that
Yeah.
sigma over epsilon, right?
yeah, but we're not going to worry about that because it would be too complicated. And, so we always, whenever we have two plates, we're going to use this approximation.
Okay.
Yeah. And just again, whenever confused, go back to the Earth and mass. Let's say this is mass M. What's the force on it? mg. How about here? Still mg. How about here? Still mg. And g is 9.8 approximately, because this distance this way is much smaller than the radius of the Earth. Yeah, when you go many kilometers upward, then yeah, it will start to be less, right? So, but for now, we're going to use the approximation, then it's fine. It's just sigma over epsilon naught and 2 epsilon. Yeah, in fact, when I say the electric field is sigma over 2 epsilon naught, is that for one sheet or both sheets? One sheet. Sigma over epsilon naught.
Two sheets.
That's if you have the two sheets between them, it's going to be sigma over epsilon. Okay, so let's do some mechanics along with electricity. Okay, so that's what the next problem is going to be. Here's the next problem. Here's an infinite sheet. It's going to have plus. Here's another infinite sheet. It's going to be minus, right? Those are the two sheets. And just to be, because whenever you do mechanics or you do Newton's laws, here is x, here is y. We always choose our coordinate system so we know what we're talking about. X is this way, y is that way. Okay, and let's say the electric field, of course it will point from plus to minus, so the electric field is in this direction. Our electric field is going to be, let's say, let's say 6 times 10 to the 5. So the electric field is 6 times 10 to the 5 newtons per coulomb. Okay? field, and of course it points. All right? Sounds good? And I need your help with this problem because I don't have the exact numbers that I'm using in the notes. Okay. Is the setup clear? So far, nothing's going on, right? There is just an electric field between two plates. Here's what we're going to do. We're going to place an electron here. Here's an electron. Electrons have a minus charge, right?
Yeah.
And as you know, the charge of an electron is minus E, which is minus 1.6 times 10 to the minus 19 coulombs. The mass of an electron is approximately 10 to the minus 30, so 9.11 times 10 to the minus 31 kilogram. Okay, that's the mass of the electron. Just given some data. Yeah.
Is it 17 or 19, the negative power?
This one?
Yeah.
19.
Oh, that's...
This is a 9. So this. That's the electron. The electron is at rest. Maybe I'm holding it. Okay. I let go. What happens? The electron will run away. Oh, I'm sorry. Yeah, no, yeah, I have it. Let me change this to be negative.
Or you can just put electron.
I could, but I need the board that way. We could change it to a proton, but let's. Yeah, protons are positive. So here it is. Sorry. Okay. And is my electric field still that way? No. All right, good. I think now it's okay, right? Yeah. Earlier you let go, nothing happens. It's stuck there. So, but now something will happen. It will run away from the minuses toward the pluses, right? The minuses repel it, the pluses attract it, so it will go to them. And the question is, the electron hits, it will reach this plate, right? What's the speed? What's the speed in this direction? What is speed? So we want to find the speed. So let me go here. So this is part A of the problem, okay? There will be part B to it. I'm going to add to it. Part A, how do we find the speed? Oh, I need to give you one more piece of information. The distance between the plates, and I'm going to use the half millimeter. So this distance is 0.5 millimeters. Okay, distance is 0.5 millimeters. So I want to know the speed of the electron when it gets to the reactor.
Is this an infinite sheet?
Yeah.
Okay.
The electric field is uniform. Yes.
Would it be 1/2?
1/2 You're thinking 1/2 v squared? Projectile? Like kinematics?
Is it the golden?
It's yeah. So we will use Newton's laws. Okay, Newton's laws. Which law do we usually use?
Second.
The second law is the one used most. It says what? F equal to
MA.
Yeah, the net force on an object is equal to the mass of that object times its acceleration. By the way, the only force acting is the electric field. We're not going to worry about gravity. Okay. So gravity is negligible. It's just the only force is the electric force. All right. What's the electric force?
Q1, Q2.
If you have 2-point charges, yes, it's K Q1 Q2 over R squared. I don't have point charges here.
So Q.
Times what?
Over R.
Q times the field. The force. Remember, why did we calculate the field? Because when you place a charge in the field, the force on it is going to be Q times E, just like M times G. Okay? So the force is going to be the charge times the electric field. Okay? That's the force. And that's equal to MA. And so A will equal to QE over M, which is minus little e times capital E over M. Now we're going to plug in some numbers, okay, to find the acceleration. Notice the acceleration is going to be constant, right? In what direction is it going to be?
Right.
The acceleration is going to be to the right. The electron will go to the right. So here it is. The acceleration is going to be this. You have your minus e, so minus 1.6 times 10 to the minus 19. You have your electric field. Your electric field is 6 times 10 to the 5th, but it's to the left. So, yeah, so it's 6 times 10 to the 5th, but it's to the left. So it's I hat, but minus. The electric field is I hat minus. And then the mass. So we get our acceleration. Minus times minus would be plus. And we need the number that's in front of the I hat. So I need some help with that.
1.05378
Okay.
times 10 to the 17.
Like this?
Yeah.
Thank you. Yeah. In exams, keep 4 sig figs. In lecture, we will just try to do, couple, maybe one. Yeah.
So we don't use sig figs based on what you give us. Like for example,
what?
the mass is 3 sig figs, and for
Yeah.
the Q is only 2 sig figs.
Yeah,
We don't
I'm
use
only
that?
keeping, yeah. In an exam?
Yeah, we use the information given, or we always use 4 sig figs.
Always 4.
Always
Yeah, always 4. Sometimes they say keep it exact, right? Assume every number I give you is 4 sig figs.
Okay.
Okay. You can always get rid of them, but if you get rid of them too soon, you can put them back. Yeah. Okay, so you get this many, it's an acceleration, so meters per second squared, right?
Yeah.
Okay, so now, what's the speed by the time it gets here? It started, the initial velocity was 0, so what's the speed when it gets to here?
Square root of 2ax.
Those motion at constant acceleration, right? Kinematics?
Yeah.
Which one? 1, 2, or 3? I don't know how you remember them.
What? 2?
Yeah. The third one. The one I call number 3. This one. V squared minus V naught squared.
Oh, that one.
Then-
Yeah, 1.5. Yeah.
That one.
I remember that one.
So the initial velocity is 0, right? Let's say this is 0, so x minus x naught is going to be this distance. It's going to be this half millimeter. So we will, v squared will be 2, 1.05 times 10 to the 17, and then x minus x naught, that's 5 times 10 to the minus 4, right? But half a millimeter is 10 to the minus 4 meters. Half a millimeter. So you need to just square root both sides, and then, so you can help me with that? You good?
I'm good. I'll say that. 100.49.
Huh?
Yeah, this Always 1.03 times 10 to the 7.
10 to the 7?
Square root.
Like this? Let's see, 17 minus 4 is 13, and then 5 times 2 is 10, so 10 to the 14 square root is about 10 to the 7. Yeah, so that's good. Yeah. Yeah, so 10 to the 7 is a reasonable number. Yeah. So that's the speed. Okay. So, good. We're going to do the next part of this problem. Okay. Yeah. So this one, v squared is just the speed. You couldn't find how long did it take, but we want, well, we will do in the next part. Next part. So here it is. This electron started at rest. It will hit this plate, right? And then it will stop. So that would be the end of it. But we want to make part B for it. So what we're going to do is, ready for the next part?
Yeah.
We're going to make a little hole here so the electron can exit.
Oh.
Yeah.
Then?
So assume the hole is so small in an infinite sheet that it doesn't change the situation, right? A small hole in the wall, it doesn't change the structure. Okay. Yeah, not very much. So it will exit, right? Our electron will exit. Here it is. Here's our electron. Okay. It's moving. What's the speed of the electron here?
The same
The
as
same
before.
thing.
The same. Is it going to slow down?
Nope.
No.
Is it going to speed up?
No.
No, because what's the force here?
Zero.
Yeah, the field is zero, so the force is zero. Good. So, but somebody came here and placed two plates. One is plus
Oh.
and one is minus. Okay?
Oh, this would be
Project.
Yeah. So that's it. The electric field now, this electric field here, let's call it E. Yeah. Yeah, let's call it E, and it's also the same size. Let's say 6 times 10 to the. I don't want you to actually think there's something special about 6 times 10 to the 5. So let's make it 2 times 10 to the 5th. Okay, like that. So nothing is really special about that. It's in the J hat direction, but minus. Right? That's the electric field. That is the electric field. And let's see how long we want this thing to be. So the distance this way, we're going to say it's L. It is 2 centimeters or 0.02 meters. So what happens if these plates were not here? The electron, if the force is 0, the velocity should be constant. It should just not change direction. But there is a net force. So the electron, will it tilt up or down? Down?
I think
Toward the
up.
minus?
Up.
Oh, up? Yeah, it has to go up toward the plus. So the electron will do this. Let's use the G right. So the electron will do this, right?
Yes.
So when it exits, it will make an angle theta.
Okay.
And the question is, basically, what's the angle theta, right? What's the angle theta? So to calculate the angle theta, who has an idea what we should do?
Yes.
Evaluate separately the velocity.
Yeah, so what's the x component of velocity when we're here? What's Vx?
It's the same.
Yeah, Vx is still gonna be this, yeah. The only thing that we will add is the y component. The y component is because there is an acceleration upward. So we would find that, and the angle would just be the tangent inverse of the y over the x. That's the idea.
So it'll become 90, that means it's like,
It becomes 90.
why?
As long as there is a little x velocity, it could not be 90. It can approach 90, but not quite. Okay, so we will find the, yeah.
Is the distance 0.02 meters?
Yeah, 2 centimeters, this way. Yes.
Oh, is it negative for the E?
The electric field is downward, so minus 2 times 10 to the 5th, yeah. So, let's do this. We will, yeah, let me use here. So I don't erase the words yet. So now the new force is this. F, again, is MA. And the force is Q times the electric field equals to the mass times the acceleration. So the acceleration will be Q times E divided by M, right? We did this earlier. And since the charge is negative, so we get minus E capital E over M. And so we plug in the numbers, minus 1.6 times 10 to the again, I will need some help with this. .51. Okay, so 10 to the 16, this one used to be 10 to the 17. That makes sense because this field is weaker than this one. So I think that's reasonable. Yeah. That's good. All right. So now I need to find the velocity in the y direction. Yeah, for the velocity, Vy will be V initial in the y direction plus the acceleration in the y direction times the time, right? What's the initial velocity in the y direction? It didn't have any, yeah, so 0. Plus, what's the acceleration in the y direction? This one. Yeah. So 3.5, 1 times 10 to the 16 times the time. Do we know how long it would take it to get across? No. But can we find it?
Yes.
Yeah. How can we find it?
Just EX over 0.
Yeah, the x velocity is constant. So the time is just the time will just be x over the x velocity, right? Distance over speed. Right? Time is distance over speed. What's the x distance that it moved? 0.02. Right? When it moves, it enters here and then it exits here. So 0.02. And then the speed in the x direction is the number we found earlier, right? 103 times 10 to the 7. So what's the time? It would be something times 10 to the minus 9 or something like that.
1.9 times 10. Oh, okay. 1.94 times 10 to the negative 9.
Thank you. Second, right?
Yes.
So that number will go here.
The first is sama terus.
Right. So what do we get for our y speed?
In the equation, is it not 1/2 AT?
1/2 AT squared?
Yeah.
That one is the other one. Yeah. Do you want me to write those equations?
No, it's
Just
fine.
to remind. Okay. Yeah, it's okay. And I've got it a while probably. Yeah. Okay. So that's the y velocity. So for the angle, theta would be what? Tangent inverse dy over dx, right?
Yeah.
And so you have so the angle will be more than 45, right?
That's close to 90.
Close to 90. How much? How close?
81 degrees.
81. Okay. Yeah.
Wow.
Yeah.
Yes. Does the charge increase as? Oh, you know what? Never mind. Not yet. I was gonna say, does the charge increase as the electron gets closer to the positive side? But it should stay even, right? Because
You mean the electric field?
as it gets closer to the positive electric field.
Yeah.
But it
The
should
electric
stay
field should
because
stay
there's-
constant.
because there's
It's
two.
uniform.
X kan konstan.
Yeah.
Apa?
It's a uniform electric field.
Oh.
Ya udah
Yeah.
hitung.
Uh,
Karena nggak ada.
That's it for this
Hey,
kind
kita
of problem. Let's see. And, well, the good news, I guess, is I'm officially done with this chapter of electric fields and charges.
81.4 ya.
If you look at the notes, I have additional solved problems, like 5 of them. I will try to go over as many as I can during discussion and lab, but I probably would not be able to finish all of them. So there are 5 of them. A couple are fairly easy, and then like 2 or 3 are more challenging. So I recommend you do them. Okay, you should do them. So after you finish the homework and you're more comfortable with this, you should do that. And by the way, the homework for this chapter, you should kind of be done with it by the end of this weekend, so that next week we're going to start Gauss's law. Okay? Yeah. Homework 6 is probably Gauss's law. Homework 5, I think. Okay, so I'm going to erase.
Are you going?
And then we're going to
I've been drinking with Chick-fil-A.
continue. Okay.
Ryan said he might not go.
It's a, oh yeah, 13 more minutes, right?
You get to work at Chick-fil-A.
You mau lihat? Ya. Contoh plottingannya.
Jadi salah hati.
What the?
So let's do a couple more examples. Here's the first one. From the additional solved problems, let's do the first one and then maybe we can do some more. Here's one example. Let's say I have a charge here,
Tapi kayaknya dia masih bagus.
plus charge, let's say it's positive Q, and another charge just like it, and it is positive Q. So both are positive.
Kan dulu.
Okay. The length is L. The length of, so 2 charges are hanging from a string, right? So this is charge Q, this is charge also Q, so they repel each other, right? So it makes sense that they make this angle.
Yeah.
Okay? And like this. And let's say the distance is R. The distance between them is R. And let's assume the angle here, these angles, this is theta, this is theta. So theta is much less than, theta is small, much less than 1. So if theta is small, you know that sine theta is almost equal to the tangent of theta. Okay? If theta is small. For example, if you have your calculator, you can put sine of 5 degrees versus tangent of 5 degrees, and you would see they're about the same. Okay? You can do sine 5 minus tangent 5. And you will get 0.0 something. Anyone wants to double check that? Okay. All right. So they're close, right? Okay. So the question is this: find R, express R in terms of Q and L, and maybe epsilon naught.
Oh.
Okay. So find R. R in terms of QL, epsilon naught, and the mass of each charge, and G. So the charge, each of them has a mass m. So gravity is this way, G. Right? Gravity pulls you down. So who remembers how to do these kinds of problems? Yes.
We have mg, or yeah, free body diagram.
Okay, free body diagram. So mg in what direction?
Down.
Down. Okay. And
L up towards the,
you mean tension?
yeah, tension.
tension, yeah, FT, and
And then
And then the
force
force.
from the other one.
the electric force, right? This way. The electric force, electric, yeah. And so the net force must be zero, right?
Yeah.
Because they are in equilibrium. And we can, again, choose your coordinate system. Here's X and here's Y. So this way you would have what? Tension times sine or cosine of theta?
Sine. Oh, cosine.
Yeah, that's adjacent. This is theta.
Yeah.
So T cosine of theta. Yeah. So in the y direction, the net force in the y direction is zero, right? So you get the tension on the cosine of theta minus mg is equal to zero, right? So the tension would just be mg over the cosine of theta. Yes? Okay, that's in the y direction. How about in the x direction? We got this way it's t sine theta, right? Okay. And then the electric force to the left and must be zero. So the tension times the sine of theta minus the electric force equals to zero. Right? The tension sine theta is to the right, electric force is to the left, so I put a minus sign to account for it being left. It makes sense, the electric force is to the left. It's repulsive, right? Plus minus. So we get this, the tension times sine of theta is equal to the electric force. The tension is mg over the cosine of theta times the sine of theta, and that's equal to the electric force. What's the electric force?
Q
K
squared.
charge 1 times charge 2, right?
Yeah, Q squared.
Q and Q, yeah. Over the distance between them squared. So R squared? Sine over cosine is what?
Tangent.
Tangent. And tangent is almost sine. Right? Sine of theta is almost tangent theta. And the reason is because cosine of a small angle is almost 1, right? Cosine of 5 degrees is basically 1. I think it's like 0.995 or something. So we can, let's continue and then we'll solve. Mg tangent of theta is equal to K. K is 1 over 4 pi epsilon naught, and then Q squared over R squared. What is R? Well, this is L, right? So we get this. Here is L. This is R over 2, right?
Mm-hmm.
And this is theta. So R over 2 is equal to R over 2 over L is equal to the sine of theta. So R over 2 is equal to L times the sine of theta. So R